So, good morning everybody. So today we are going to look at the comparative study of S&P block elements, BCH3103. Your facilitator is Esther Ndungo. So the periodic table is divided into 4 categories. The first two groups, group 1 and group 2, are called the S block elements. The middle elements here from group 3 to group 12 are called the D block elements, while from group 13 to group 18 are called the P block elements. And there is another category here that we call the F block elements. So the way these elements are arranged depends on the electronic configuration of the element, where the last what determines whether the element will be in P block, D block or S block is the position of the last electron in the valence configuration. So if the last electron falls into the P orbital, then that element will belong to the P block category. If the last electron is positioned in the D orbital, then that element will be in the D category. And if the last electron is in the S orbital, then that element belongs to the S block elements. Now, the S and the P block elements are also called the main group elements. So this category of elements and these ones, they are called the main group elements, while the D block elements, the ones in the middle of the periodic table, and these ones at the bottom, the lanthanides and the actinides, are called the F block elements. So in this unit and for this lecture, I will focus on the S block elements, that is the group 1, and the group 2, that is the alkali metals and the alkaline earth metals. And I'll also look at the group 13 elements, the boron group of elements in the P block category. So like we have said, the periodic table is segregated into S, P, D and F blocks, and that depends on where the valence electron is placed. So if the last electron is in the S orbital, then it will be in the S block. If the last electron is in the P orbital, that will be a P block element. If the last electron in the configuration is in the F orbitals, then it will be in the F block category. So the S block elements are the alkali metals and the alkaline earth metals. The alkali metals have only one electron in the valence orbital, while the alkaline earth metals have 2 electrons in the valence S orbital. The alkali metals are the first elements, they're the first elements in every period. If you go to period 2, lithium is the first element. If you go to period 4, potassium is the first element. And we go to period 1, of course, hydrogen can be placed either in group 1 or in group 7. So because it can either gain 1 electron like the halogens, or it can lose 1 electron like the alkali metals. So the first element of every period is the belongs to the alkali group of alkali metals. So the alkali metals include lithium. If you look at the configuration, they all have S1 in the valence configuration. We have lithium, we have sodium, we have potassium, rubidium, cesium, and francium. So the alkali metals have the biggest atomic radius in the periodic table. That also means that they are the most reactive elements in the periodic table. So things like sodium, potassium, we store them in paraffin because they are very, very reactive even in air. Then the alkaline earth metals, we have beryllium, magnesium, calcium, strontium, barium, and radium. So in the configuration of the alkaline earth metals, the valence configuration has S2 configuration. So the alkaline earth metals are the second most reactive elements in the periodic table. So the alkali metals, they do not occur free in nature. They are very, very reactive, and so you cannot find them free in nature. So they always occur in combined state, because if let's say you leave potassium just you place potassium on the table, it's going to react with oxygen to form oxide. Then it can absorb water from the atmosphere to form hydroxide. Then we know that the potassium hydroxide and sodium hydroxides, they're able to absorb carbon 4 oxide. So again, it can absorb the CO2 to form a carbonate. So these elements, because they're very, very reactive, then they do not occur free in nature. The other thing, because of their high reactivity, the alkali metals cannot be obtained by electrolysis of their aqueous solution. This is because in aqueous solutions we have the water molecules, so we'll also have the hydrogen ions and the hydroxyl ions, which are preferentially discharged at the electrode. So if you have aqueous sodium chloride, whatever will be discharged on the anode is not the chloride but the oxygen gas, and whatever will be deposited at the cathode is the hydrogen. So we do not obtain these elements by electrolyzing their aqueous solutions, but normally we use their molten salts, because in their molten salts then we do not have interfering anions during the electrolysis. So both alkali metals and alkaline earth metals, they show regular gradation in their properties among their respective group elements, so that if it is like the atomic radii, it increases regularly down the group. If it is the ionization energy, it decreases regularly down the group. So they normally show a regular gradation in their properties. The reason why we have to mention this is because when you go to the P block elements and even the D block elements, you'll find that the properties do not change regularly down the group. The other thing is that the first member of S block elements, that is lithium and beryllium, they differ very much from the rest of the members. So you'll find that the first element of every group, be it group 1, group 2, group 3, group 4, the first element always shows anomalous behavior from the heavier congeners. So lithium and beryllium, they do not show similar properties, or they differ a bit from the other S block elements in terms of their behavior. For instance, sodium carbonate cannot be decomposed but lithium carbonate can be decomposed to lithium oxide, carbon 4 oxide, and carbon 4 oxide. Lithium nitrate also decomposes completely to lithium oxide, nitrogen 4 oxide, and whereas and oxygen. On the other hand, if you look at the nitrates of the other alkali metals like sodium nitrate, it decomposes to give sodium nitrite. So the first members of a group, they behave abnormally, or they show anomalous behavior from the rest of the group members. However, they show semblance, or they show similarities with members of the next group, which they are diagonally placed. For instance, lithium shows more similarities with magnesium. Beryllium shows a lot of similarities with aluminium, and also boron shows a lot of similarities with silicon. So you'll find that some properties of lithium, they differ a lot from those ones of sodium. Like the way we've talked about the salts, the nitrates, how the lithium nitrate decomposes completely, how lithium also reacts with nitrogen to form lithium nitride, while none of the other alkali metals are able to form nitrides with sodium. The same case is observed with beryllium. So you'll find that beryllium shows a lot of similarities with aluminium. For instance, the oxide of beryllium, beryllium 2 oxide, is amphoteric. That is, it can react with both acid and base, at the same time, aluminium oxide is also amphoteric. On the other hand, if you look at the other group members like magnesium, calcium, their oxides are purely basic. So the first element of a group normally shows anomalous behavior from the rest of the members, but it shows some similarity with elements in the elements of the next group, which are placed diagonally, and that is what we call the diagonal relationship. So the reason why the first elements of a group, be it group 1, 2, 3, 4, 5, 6, 7, differs from the rest of the members is because the first element normally has low atomic and ionic size. They also have a greater charge density. They also have high polarization power, and they also lack the d orbitals. So because of that, these properties, they make the first element of every group to show some abnormalities or abnormal behavior compared to the other heavier congeners. So the greater polarization of S block elements makes the first element to be more covalent. So you'll find that lithium forms covalent compounds, whereas all the other alkali metals, they form ionic compounds. So, lithium being an alkali metal, and it's forming covalent compounds is because of its small atomic size, high polarization power, high effective nuclear charge, and so it forms covalent compounds which even dissolve in organic solvents. The same thing is observed with lithium. So you find that lithium also forms covalent compounds, while all the other elements in group 2, they form ionic compounds. So we are saying that the size and the charge density of lithium is much similar to that of magnesium. So there is more similarity between lithium and magnesium than there is between lithium and the other group 1 elements. The physical and chemical properties, they change in a particular trend as the atomic number increases. So as we move down the group, the atomic number increases, and once the atomic number increases, it also means that the atomic radii increases. So with an increase in atomic radii, then the ionization energy is low, and if the ionization energy is low, that makes the reactivity of the alkali metals to increase down the group. So when it comes to metals, they react by losing electrons, and so the more easily an element can lose electrons, then the more reactive it's going to be. And that's why you'll find that the group 1 elements, you cannot just leave them exposed in air and then you find them in their pure state. They'll have reacted because they easily lose their valence electrons. The other thing is the ionization enthalpy. The ionization enthalpy is the energy required to remove an electron from a gaseous atom. So as we move down the group, as the atomic radii increases and the shielding effect increases, then it becomes easier to lose an electron, and so the ionization enthalpy or the ionization energy also decreases down the group as the size of the atom increases. So the alkali metals have the lowest ionization energies because they have the biggest atomic radii in the periodic table. So you'll find that if you compare the alkali metals and the alkaline earth metals, the alkaline earth metals have much smaller atomic radii, and because of their smaller atomic radii, that means the valence electrons are more closely attracted to the nucleus, and so you'll find that the ionization energies of group 2 elements are slightly higher than the corresponding group 1 elements. The other thing is the hydration energy. The hydration energy, as the size of the atom becomes bigger, then it becomes more difficult for that particular atom to attract water molecules towards itself. When the size of the atom, or when the atomic or ionic sizes are smaller, then the atoms are able to attract water molecules towards themselves, and so they become hydrated. So the hydration energy decreases down the group as the size of the atoms increase. So the bigger the atomic radii, the lower the hydration energy. Now, because of this hydration enthalpy, you'll find that when you have lithium ion in solution, we would expect because lithium is the smallest, lithium ion is the smallest cation in group 1, we would expect it to, to be the best conductor of electricity in solution because it's small, and so its mobility should be, quite high in solution. But that is not the case. You normally find that lithium ion in solution, it absorbs or it attracts water molecules. It has a high hydration energy, so it attracts water molecules towards itself. Then the cation becomes bulky, and so the movement in solution becomes difficult. So that's why you'll find that the conductivity of lithium in solution is much lower than would be expected. On the other hand, the bigger cations like cesium, the cesium ion, that one is not readily hydrated. It does not readily attract water molecules towards itself, and so you'll find it's a much better conductor because it can move more freely in water. So the smaller the size of ion, then the hydration enthalpy is high because the atom has a capacity to accommodate a larger number of water molecules. So the S block elements, in the S block elements, the density of the alkali metals increases down the group. Also, the alkali metals have low melting points and boiling points because of the weak metallic bonding. You see, these elements have very big atomic radius. So with big atomic radius, then the metallic bonds are weak. So if the metallic bonds are weak, then the melting points and the boiling points are much lower. The alkali metals have the lowest melting points and boiling points in the periodic table. So when the size of the atom atom is much smaller and the effective nuclear charge is high, then the metallic bonds that are formed are normally strong, and the melting points and the boiling points also are high. So because of this, because of having these weak metallic bonds, that's why we can be able to cut sodium with a knife, potassium with a knife. So the alkali metals are very soft. They are very soft because of their big atomic radius and the weak metallic bonds. Now, the other thing is that the alkali metals and their respective salts have the capability to impart color to the oxidizing flame. So you'll find that all the alkali metals are able to impart a characteristic color to the flame. This is normally because the flame energy is enough to excite the valence electrons in the alkali metals to higher energy levels, and so when it comes back to ground state, it releases, when the electron comes back to ground state, then it releases energy in form of electromagnetic radiation in the UV visible region. So that's why you'll find that the alkali metals can also be, they can be analyzed using the flame test. You can analyze them using the flame test. The same is true with the alkaline earth metals. The alkaline earth metals also impart a characteristic color to the flame for the same reasons, that the flame energy is enough to excite the valence electrons to higher energy levels, and so when the electrons come back, they release energy in form of electromagnetic radiation. That's why you find that calcium has a crimson, gives a crimson red color, sodium burns with a yellow color, etc., etc. But in group 2, beryllium and magnesium, they do not give a characteristic color to the flame. This is because they have much smaller ionic and atomic radius. Because of their small atomic and ionic radius, then the outermost electrons are strongly attracted to the nucleus, so that the flame energy is not enough to excite the electrons to higher energy levels. So when you burn magnesium in flame, it just burns with a bright flame, but it doesn't give a characteristic color in the UV visible range of the electromagnetic spectrum. So for you to excite the electrons in beryllium and magnesium, you require more energetic flame or more energy to be able to excite them to higher energy levels. So the diagonal relationships, we'd already looked at them. Lithium shows a lot of similarities with magnesium, beryllium with aluminium, and boron with silicon. Boron is in group 3. So some of the so we're saying the diagonal relationship exists between adjacent elements which are located in the second and third period of the periodic table. So lithium shows similarities with magnesium, And some of the similarities between lithium and magnesium is, first of all, is the hardness. Lithium is a very hard metal compared to the other alkali metals. The chlorides of lithium and magnesium have capability to be soluble in ethanol, while the chlorides of the other elements, group 1 elements, are not. They are also much lighter compared to the other elements in their groups. Lithium and magnesium react gently with water, and also the oxides and hydroxides are less soluble in water. So if you place an alkali metal like sodium, potassium in water, it reacts very vigorously, juts around, jumping around. It reacts very violently with water. But when it comes to lithium, lithium reacts very gently with water. In presence of nitrogen, lithium and magnesium form nitrides. Only lithium can be able to form nitrides in group 1. The other one, the superoxides, are not formed when lithium and magnesium react with excess oxygen. So lithium does not form superoxides, while all the other group 1 elements are able to form superoxides. The other thing is that carbon dioxide and their respective oxides are formed when carbonates of magnesium and lithium are heated. So we had also seen this, that the carbonates of group 1 elements are not, you cannot be able to decompose them, but the the carbonate of lithium decomposes completely to give carbon 4 oxide. The other one, beryllium. Okay, so yeah, so that is some of the examples of the diagonal relationship between lithium and magnesium. Now, beryllium shows similar properties to aluminium, which is on the 3rd period and the 3rd group. So again, lithium will show diagonal relationship with aluminium. For instance, aluminium hydroxide, they react with excess alkali to form respective ions like aluminate ions and beryl ions. Both the elements have the capacity to withstand the acid attack due to presence of oxide film on the surface of the metal. So both metals, they form an oxide film, and so they can be able to withstand acid attack. Both metals have a tendency to form complexes. Now, beryllium and aluminium are both able to form complexes, unlike the other group members. Because beryllium has a very small atomic radii, it has a high effective nuclear charge, then it can be able to attract negatively charged ions to form complexes. The other point is that the chlorides of both these metals possess the capacity to be soluble in organic solvents. Remember, beryllium and lithium, they form covalent compounds. Now, covalent compounds are able to dissolve in organic solvents. So that also tells you that the chloride of aluminium is also covalent in nature. So those are the group, those are the group 1 and the group 2 elements, their general properties. So now we're going to look at the group 13 elements, and group 13 elements are the first one in the P block category. So the group 13 include boron, aluminium, gallium, indium, and thallium. So these are the elements that we will be looking at in the P block category. So So group 13, they belong to the P block in the periodic table. So they're the first ones in the P block. And they also have properties like the amphoteric character and variable oxidation states, which are also going to be seen with the other P block elements. So they have a configuration of NS2, NP1. So they have 2 electrons in the s orbital and 1 electron in the p orbital, and they adopt the +3 oxidation state in their compounds. So when it comes to the oxidation state of the group 13 elements, the general oxidation state is +3 and +1 oxidation state. As we go down the group, the tendency to form +1 ion increases due to inert pair effect. So the +3 oxidation state is formed when we lose the s2, the 2 electrons in the s orbital and the 1 electron in the p orbital, and that is why we form the +3. That is the group's oxidation state. On the other hand, as we move down the group, as the atomic number increases, then the d orbitals are filled with electrons and also the f orbitals. So you're going to find that because the d orbitals and the f orbitals have very poor shielding properties, then they tend to attract the s electrons closely towards, they tend to attract the s electrons strongly towards the nucleus, and with that strong attraction, the s electrons become less reactive. So that situation where the s electrons do not participate in bonding is called the inert pair effect. So the 2 pair of electrons become inert, or they become unreactive in a chemical reaction. So with that, you will find that boron and aluminium are more likely, they normally form +3 oxidation state compounds, while as we move down the group towards the thallium, then thallium has a high tendency to form predominantly +1 oxidation state compounds. So we're saying as we move down the group, the tendency to form +1 increases, +1 ions increases. And this is because the s orbitals do not participate in chemical bonding because of the poor shielding of the intervening electrons. Now in thallium, d and f orbitals are filled with electrons, and the shielding capacity of the d and f electrons is very poor. Therefore, the nuclear charge that is able to seep through and attract the s orbitals closer, making the s orbitals reluctant to bond. So just like with the alkali metals and the alkaline earth metals, the covalent character of the group 3 elements is shown especially with boron. The smaller the size of the atom and ion, the smaller the atom and ion is, the more it is likely to form covalent compounds. So as we move down the group, the bonding will vary from ionic bonding as the atomic radi increases. So as we move down the group, then the bonding becomes more ionic as the size of the atom becomes bigger, and so that losing an electron becomes easier. Now boron, it forms predominantly covalent compounds, while thallium forms ionic compounds. So that is obviously because of the difference in atomic radii. Now boron is essentially non-metallic, while the heavier members are distinctly metallic. So boron behaves 100% like a non-metal, because when you react boron with an acid, it forms boric acid, whereas we know with the other elements, if you have say aluminium plus hydrochloric acid, you form a salt and hydrogen gas. But boron, when you react it with acids, it forms boric acid. So it's very much non-metallic. So boron is non-metallic, while the heavier members are distinctly metallic. Now, boron behaves differently from the other group members because, one, it has a very small size because of its small atomic radii and ionic radii. The other thing is that it has a high ionization enthalpy, so that losing electrons is difficult for boron. The other thing is that it has high electronegativity owing to its small size. So because of its small atomic and ionic size, then it has a very high electronegativity. Also, it lacks the d orbitals in the valence shell. At the same time, boron has pronounced diagonal relationship with silicon. That is, it has a lot of similarities with silicon, which is in group 14 rather, silicon in group 14. So they both form acidic oxides. Boron oxide and silica are both acidic oxides. The other thing is that they form gaseous flammable hydrides. So the hydrides are gaseous, while the hydrides of something like aluminium, they are solid in nature. They both form many polymeric oxide structures, so they form polymeric oxides. Yeah, so these are the group 13 elements. You have boron. As you can see in their configuration, we have S2P1 in all the configuration. We have S2P1 boron, aluminium, gallium, indium, and thallium. Now, if we look at the atomic radius of boron is 85 picometers, aluminium is 143, gallium 135, indium 167, and thallium 170. So when we were looking at the alkali metals and the alkaline earth metals, there was that sort of uniform increase in atomic radii, but with the group 3 elements, the increase is not so uniform. Between boron and aluminium, there is the normal increase in atomic radii because of the increase in the number of electrons and the increase in the number of energy levels. However, between aluminium and gallium, there is increase, but it's not so much, because in gallium we are filling in the 3d. The d orbitals have poor shielding effect, and so because of the poor shielding effect, the outermost electrons are strongly attracted towards the nucleus. So you'll see that between aluminium and gallium, the atomic radii decreases from 143 to 135. That is not what we would expect, because the atomic number is increasing. Now, between gallium and indium, there is the normal increase in atomic radii because both of them, the d orbitals are filled. But between indium and thallium, the atomic radii increases minimally, because in thallium, now we are filling in the 4f orbitals with 14 electrons. The f orbitals have very poor shielding properties, and so once you add f electrons in an atom, the overall effect that is felt is the increase in the effective nuclear charge, and that is what we call the lanthanide contraction. So between lithium, indium and thallium, we have lanthanide contraction, and that is why the atomic radii increases only minimally. So the same case with ionization energy, it is not so uniform. We would expect it to decrease uniformly down the group, but then between boron and aluminium, there is the normal decrease, and then aluminium and gallium, the decrease is very minimal. Between gallium and indium, there is a normal decrease, and between indium and thallium, the ionization energy increases. So of course this is not the normal pattern we would expect, and those differences are brought about by the presence of the d orbitals and the 4f electron orbitals. If you look at the electronegativity, boron has the highest electronegativity, and that is why it tends to form covalent compounds. Melting points, of course, boron has the highest melting point because it has the smallest atomic radii, and of course it has the highest boiling point. The boiling point decreases down the group. So these are the group 13 elements: the boron, aluminium, gallium, and indium. So the atomic radii and ionic radii, they increase because of addition of new, we are adding a new shell, but there is a deviation, between gallium and aluminium because of the poor shielding of the d orbitals, and also between indium and thallium, the increase is not as expected. Again, the ionization energy does not increase smoothly. From boron to aluminium, the ionization will increase as expected, but from aluminium to gallium, it increases slightly. And the fast ionization energy of thallium is even greater than that of aluminium because of lanthanide contraction. So like we had mentioned earlier, boron has the highest electronegativity, and the electronegativity decreases down the group as the size of the atom increase. So as we move down the group, there is increase in shielding effect, and with the increase in shielding effect, then the electronegativity also decreases. Now, the electropositivity, it also does not increase uniformly down the group. The trend that is expected is the opposite of electronegativity. The metallic, it increases first from boron to aluminium, then it decreases, and then it decreases slightly from aluminium to thallium. So the electropositivity is because the group 13 has very high ionization enthalpy. Remember, we are moving across the period, and as we move across the period, the effective nuclear charge is increasing. And so when the effective nuclear charge increases, then the atomic sizes, they also become smaller. So so that is why they have higher ionization energies compared to the S block elements. So when we look at the chemical properties of group 13, all the group 13 elements, they react with oxygen at high temperatures to form the trioxides. And the trioxides of, on top of the trioxides, thallium, because it is more stable in +1 oxidation state, it also forms the thallium-1 oxide. But all the elements are able to form the group's oxidation state oxide. Now the reactivity towards oxygen increases down the group because the bigger the atom is, the more it will easily lose electrons and react with oxygen. Now boron is unreactive towards oxygen in its crystalline form, but if it's finely divided, then it reacts with oxygen to form boron 3 oxide. The aluminium normally forms a layer with oxygen, a protective layer of aluminium oxide on its surface, and that is why it is a bit inert. That is what makes it unreactive. So aluminium reacts with oxygen to form aluminium 3 oxide, and so are all the other elements. Now when we dissolve the oxides of group 3 elements in water, then we form the hydroxides. So all the metals, where M is any of the metals, it could be boron, aluminium, thallium, gallium, indium, all of them, they're able to form metal hydroxides. And the basic character or the basicity of the metal hydroxides increases down the group. Now boron hydroxide or boric acid is the most acidic, and aluminium hydroxide is amphoteric, meaning that aluminium hydroxide can react with both acids and bases. So if you react, aluminium hydroxide can react with an acid to give you aluminium 3 ions, and it can also react with a base to form the aluminate ions. So the basic character of the group 13 elements increases down the group. Now boron does not react with non-oxidizing acids like hydrochloric acids, but at higher temperatures it reacts with oxidizing acids like a mixture of hot conch, sulfuric acid and nitric acid to give boric acid. So if you react boron with nitric acid, you'll get boric acid and nitrogen 4 oxide. The other thing is that boron resists the action of alkalis. Boron resists the action of alkalis, but the other group 13 elements, they all react with alkalis like sodium hydroxide and potassium hydroxide to liberate hydrogen gas. So boron plus potassium hydroxide, you get potassium borate and hydrogen. All the other elements, they react with both oxidizing and non-oxidizing acids to liberate hydrogen gas. Now when you react aluminium with nitric acid, it oxidizes, it forms a protective layer of aluminium to form aluminium oxide, and that protective layer makes it unreactive or passive. Now all the group 13 elements react with halogens at high temperatures to form the trihalides. Now so where M is any of the group 3 elements, if you react it with a halogen like chlorine, bromine, then you're going to get the metal trihalide. Now thallium, on top of forming the trihalides, it also forms the monohalides, and the monohalides are the most stable for thallium. Now the trihalides of boron is also able to form complex trihalides on top of the normal trihalides. And also the aluminium trichloride exists in form of a dimer. It is a dimer in form of M2Cl6, the same case as gallium-3 chloride. Both of them are dimeric in nature. And boron, because of its small atomic radii and high polarizing power, it also forms complex halides like tetrafluoroborate. So the reactivity towards water, boron does not react with water or steam, but at elevated temperatures it can react with steam to form boron 3 oxide. Also aluminium decomposes water to give hydrogen gas if there is no oxide layer on its surface. Thallium forms thallium-1 hydroxide because thallium is most stable in the lower oxidation state, that is the +1 oxidation state. Now, when it comes to the reactivity towards metals, you'll find that only boron combines with metals to form borides. So boron is totally non-metallic. So it reacts with other metals just like the way sulfur can react with a metal. You can react magnesium with sulfur to form magnesium sulfide. So the same case, if you react magnesium with boron, then it forms magnesium boride. So this is only true to boron in group 13. Among the group 13 elements, only boron reacts with other metals to form a chemical compound. So when it comes to the tendency to form complexes, the group 13 have a higher tendency compared to the S block elements because the group 13 elements are small in size and they also have a high polarizing power. So with that in mind, they can easily attract electron donors towards themselves in order to form complexes. So boron has the highest ability to form coordination complexes, for example tetrafluoroborate, and the tetrafluoroborate has an sp3 hybridization with a tetrahedral geometry. Now, the other elements are able to form complex compounds, for instance, lithium, aluminium hydride, sodium borohydride. So all those are also complex compounds. Now, group 13 elements, they react with hydrogen to form ionic hydrides. So, and they are also able to form complex hydrides. Two of the most well-known complex hydrides of group 13 are the borohydride and aluminium hydride. So if you react aluminium hydride plus lithium hydride, you will form lithium aluminium hydride, which is a complex hydride that is used a lot in organic synthesis, especially in the reduction of the carbonyls. The same case with borohydride. If you react boron chloride plus lithium hydride, then you're able to form lithium aluminium hydride, which again is used in organic synthesis for the reduction as a reducing agent. Now, the boron hydrides are extensively used as reducing agents, and binary compounds between boron and hydrogen are called boranes. And the simplest borane is the diborane. These boranes, they behave just, they form long chains just like the alkanes. They say that it is the same way you can have methane, ethane, butane, propane, like that. So also these boranes, you know, they can also be able to form those kinds of chains similar to those of carbon. So the boranes are classified into three major types. We have the closoboranes, where you have Bn, H2n plus 2. You have nidoboranes, where you have Bn, H2n plus 4. And you have arachnoboranes, where you have Bn, H2n plus 6. So the boranes are important as reducing agents in the laboratory. Now, the diborane can be prepared from boron chloride. You react it with hydrogen in an electric furnace, then you're able to form your diborane. So if you heat diborane on heating alone or in presence of hydrogen, then you can be able to get the higher boranes. So the simplest borane is the diborane. That is the end of the lesson. Thank you very much.
We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.